Okay, welcome everyone. I think we still have a couple more people will be filing in, but we'll just go ahead and get started right now. So I'd like to welcome you to today's webinar. The topic is Differential Via Optimization with Ansys HFSS 3D Layout and optiSLang. So before I introduce today's presenter, I'd like to go over a few housekeeping items. All callers have been muted to prevent some background noise, and there's going to be a question and answer segment at the conclusion of today's webinar. If you have a question about any of the material presented today, simply submit a question via the Q&A tab at the bottom. We will attempt to answer all questions at the end of the webinar. However, in the event we run out of time, questions may be answered via email within the next few days. Please ask your questions early so that we can get them queued up and ready to go for the Q&A. You may move the presentation to a full screen view by putting on this option at the top of the shared screen on the floating panel. Today's event is being recorded. You'll be able to view the recording in about a week's time on Ansys's website. Select the resource library button located in the menu at the top of the homepage. So without further ado, I'm going to introduce our expert today. This is Peter Krenz. He's a lead application engineer at Ansys. Peter has a focus on RF and SI applications using our high-frequency electromagnetic simulation tools with more than 8 years of experience at Ansys. Peter has a MS and PhD degrees in optics from the University of Central Florida and held a postdoctoral research position with the Center of Nanoscience and Technology at the University of Notre Dame. So please enjoy today's event. We'll control the movement of the slides, and I will hand it over to Peter.
Thank you very much. And welcome to the webinar. My name is Peter Krenz, and I will be talking to you today about how we can optimize the differential via that was analyzed in HFSS 3D layout using optiSLang. For the webinar today, what I'm planning to do is first give you a very quick overview of the tools that we're using. So we'll start off talking a little bit about HFSS 3D layout and a little bit about optiSLang. And then I want to spend the bulk of the webinar on the optimization part, where we're actually looking at how can we improve the differential return loss of this via. And in the second part, I want to take a closer look at the robustness analysis, which will actually tell us what is the yield that we can expect given certain manufacturing tolerances if we now go and take this optimized via and put it into production. So to start things out, what is 3D layout? And I've heard that many of you are already using HFSS 3D layout, so hopefully this is just a very quick review for you. But what it really is, it's our 3D electromagnetic solver. It's based on finite elements, and this one is really targeted for our layered structures. And by layered structures, I mean anything that is similar to PCB, so it could be package, or to some certain extent also once we're looking into the chips that might be on a board. But it's everything that's described with a certain layered information. And that's really where it differentiates itself from just the common HFSS that we use for other applications, which uses the more traditional MCAD interface, where we describe objects in terms of boxes, cylinders, and spheres. So within 3D layout, everything we're dealing with is defined based on, as I said, things that are similar to printed circuit boards. So we have a layer stack up, which defines that each layer has a certain thickness, and everything on that layer will have very specific material properties. If we want to edit something on the board, changing the layer thickness, for example, that's just a button click to do here. If we're looking at via definitions, we can easily update them by changing pad stack definitions that are then applied to all the other vias that use the same definition. So it makes it very easy and convenient to interact with this kind of geometry. And then when we're solving it with the HFSS solver, we're not taking any shortcuts. We're not assuming that dielectrics are infinite in size or the metal layers have zero thickness. So we're analyzing everything the way that it's defined within the geometry. I should also mention that from the 3D layout interface, we have access to other EM solvers, mainly the SI wave solver and also a method of moment solver, which is our planar EM solver. And through the same interface, we can also set up time domain circuit level simulations. The other tool that we're using here is optiSLang. And when I first heard of optiSLang, I really thought it was just an optimization tool that kind of just sits there by itself, interacts with certain solvers. But there's a lot more to optiSLang. So first up, we can use optiSLang to fit or calibrate our simulations to measurements. And as an example for that is if you've done a lot of measurements and maybe you're not really sure about what material properties are in your device, you can set up a simulation with variables assigned to those material properties and then do the fit or the calibration to essentially calculate what material properties your device has and extract them out to know what the physical device used in terms of material properties. The other aspect where optiSLang is very powerful is for understanding how the design works, and we're doing that with a sensitivity analysis, where we really understand which parameters have a large influence on the output of the device and which ones might not be important at all. And that information, of course, can be very important when we're trying to optimize the design, which is done with the design improvements or the optimizers that are built into optiSLang. And the last part here in the circle is the design quality analysis with the robustness or reliability module. And here we're looking at not only design for Six Sigma, but also looking at what I had mentioned earlier, right? Looking at the how the manufacturing tolerances might impact the yield of manufactured devices. The other part where optiSLang is really strong in is in terms of building a simulation workflow. So if, for example, you have an HFSS 3D layout simulation, and then you have certain Python scripts that you're running at the end to extract certain information out of the data that was generated by that solver, we can very easily set up those nodes within the optiSLang workflow and have them connected to each other and then wrap all that into an optimization, for example. So it's one of the things that I very much overlooked when I first learned about optiSLang, but it's another strong suit it has to couple solving tools together. And this can be not only solvers, but also post-processing tools. I mentioned maybe a Python script, something that could be written in-house, or maybe MATLAB scripts could be something else. So with this quick introduction out of the way, let's take a close look at the via optimization. The via that we're talking about here is a differential via in an 18-layer PCB. We want to connect coupled microstrips on the first layer to coupled strip lines on the 7th layer. And the substrate for all these layers is FR4. So it's a affordable substrate, but unfortunately, usually it has a lot of losses associated with it. And so trying to optimize the design here might be very important to really get all the performance out of this via that we possibly can get out of it. For the optimization goal, what I'm going to be looking at here is the differential return loss. And over the entire range, 0 to 40 gigahertz, I want to minimize it. And one of the design requirements that I was handed to from my manager says that this via has to have a differential return loss that's better than minus 13 dB. When I first drew up this geometry, I solved it in 3D layout and I find exactly the curve that I'm showing down here. And so my initial design has a maximum differential return loss of about minus 5 dB. So it has a long ways to go in terms of improving it. Of course, there are many different approaches that we can take when we want to optimize a design. And what we're doing here in optiSLang is we're focusing on gaining the most insight into the design. So it's not just a blind black box optimization where we're throwing in the design and hoping for the optimizer to return the best possible design for us. So we're actually going to take a few steps in this optimization approach, and we're going to be starting off with a sensitivity analysis. And with this, we're really ensuring that we're exploring the design space as accurately as we possibly can. And that ensures that we're not getting stuck on a local optimum, but we're really finding the global optimum in our design space. And from this, we also get insight about what input parameters have a large impact on the output and which ones we might be able to ignore entirely. Throughout the sensitivity analysis, we're actually creating a meta model. And using this meta model, we can also run a very quick optimization just to see if any of the designs that are predicted by this meta model might fare better than any of the designs that we had previously evaluated during the sensitivity analysis. And at that point, we have to take a step back and just ask the question, are the designs that we found here, are they good enough? Do they meet the design requirements that we're after? Or do we need to spend more time to get a little bit more performance out of this design? And if we want to get more performance out, we can run a direct optimization. And here we're not running a direct optimization blindly on the design that we started out with, but we're actually using all the insight that we gained from the sensitivity analysis. And we're using a much reduced design space to ensure that the direct optimization can be run as quickly as it possibly can. And we're really focusing in on the global optimum. So let's take a closer look at what a sensitivity analysis is in optiSLang. The way that it works is we're starting off by defining the design space. So each input parameter can be varied over a certain range. And optiSLang will create a design of experiments for all these input parameters. Then we take all these designs, send them off to 3D Layout, and have that evaluated for us. 3D Layout then will return to us in optiSLang all the outputs of those designs. In our case, that will be the maximum differential return loss. To that, optiSLang will fit a meta model, and a meta model is really just a mathematical model that we can use in place of evaluating the simulations in 3D Layout. So it's much, much quicker to obtain information about how a certain design would perform. So for a certain input, what kind of differential return loss would we get? You may have heard a meta model under different names. Sometimes it's called a response surface, sometimes a reduced order model, sometimes just a transfer function. But once we have this meta model, we can quickly study the design space, and then optiSLang can give us information about which of the input parameters have the largest impact on the output. So in our case, again, the maximum of the differential return loss. Let's take a closer look at the meta model that optiSLang creates for us. We call it the meta model of optimum prognosis. And you should know that optiSLang was first developed in Germany. And in the German language, whenever we talk about prognosis, that actually really implies more predictability. In English, of course, I always think that prognosis means something when you're going to the doctor. But so in the future, whenever you hear prognosis in the context of optiSLang, always think predictability instead. And there are different ways that we can create a meta model. So the easiest way, if we have a certain set of data, and here we have just a very simple example, so just a 1D example, one input, and we're looking at the response, we can just very easily fit to the existing data. So the existing data is predicted with very high accuracy, but if we now add additional data, we're asking the meta model to predict data at points that were not included in the meta model creation, that accuracy might not be as good. And so optiSLang takes a different approach to creating the meta model. We actually have multiple meta models that we can use, anything from a linear model, a quadratic polynomial could be fitted to the data. We have Kriging models. There's also more advanced models that are based on machine learning, all just in the scope to create a good way to predict what data could look like for certain inputs of our design. And when we're creating the meta model, we're actually going to ignore a subset of the data. And by ignoring that subset of the data, we can then add the data back in and use that as a measure of how well the meta model was actually able to predict that data that wasn't part of the meta model generation. And that all fits into a coefficient that we call coefficient of prognosis, COP. So again, think about coefficient of predictability. And that's a figure of merit that we're using here to assess how good the meta model can actually predict data in the design space that we haven't explicitly solved for. And so in this example, we're seeing that just this polynomial fit does a really good job of predicting the data that's here in black and blue. So this would be a meta model of optimum prognosis in the optiSLang speak. optiSLang uses an adaptive approach to continuously improve the accuracy of the meta model as we're getting more data available for it. The differential via that we're trying to optimize here, I have it defined with 9 parameters that control all aspects of the geometry. So via, pad, anti-pad size, the spacing between the vias. If we're looking from a top-down view, we can see that the taper length for the microstrip and the strip lines are also controlled, along with the dog bone cutout. And then on the side view, we're seeing that the radius of the back drill is also controlled with a parameter. For the initial design, I already mentioned that it doesn't perform too well. The maximum differential return loss is at minus 5 dB. And again, the design requirement says that we need to be better than minus 13 dB. For the optimization goal, I'm just going to look at the entire frequency range. I don't care at what frequency the maximum occurs. I'm just going to pick out the maximum value, which in this case is right around 35 gigahertz. And I'm going to report this one back, and I want to minimize that value as much as possible. To integrate 3D layout into optiSLang, we have different ways of how we can generate an optiSLang project that includes the 3D layout design. We can do that out of the electronics desktop with an ACT wizard, or actually directly out of the Optimetrics entry. Or what I'm showing here, we're starting off with a new optiSLang project and then using the drag and drop operation to drop the solver wizard onto the optiSLang scenery to generate this integration. And that produces what we call a parametric solve system, where the input for the parametric solve system are all the 9 different parameters that I had defined in 3D layout that control the geometry of the via. And as the output, we have the maximum of the differential return loss. Now to start the sensitivity wizard, to set up the sensitivity analysis, we just drag and drop the sensitivity wizard onto the parametric solve setup. And that will guide us through all the steps needed to set up the sensitivity analysis. First up, we define the design space. So this is the minimum and maximum bound of all the input parameters. So we define what range they can take on. Next up, we define the optimization criteria. So here I specify that I want to take my maximum differential return loss, and I want to minimize it. The other aspect that we can define here is we can add constraints. And here I have a physical constraint that says that my via diameter and the pad size on top of it should always be smaller than the spacing between the signal vias. And having a constraint like this ensures that I don't generate any designs that might create some undesired output. So in this case, it would short out the signal trace. I don't want that. And I can actually have it set up so that optiSLang won't send these designs to 3D layout to have those evaluated, because it just would produce nonsensical data that won't help us in terms of optimizing this design. The other part here will be the AMOP setup. So it's the adaptive meta model of Optimum Prognosis. And in terms of how we define the setup for it, we start out with an initial sampling, and then we refine that sampling with this adaptive process. And here we can specify with sliding bars what's important to us. So here, my most important aspect will be focusing on the optimization criteria. So making sure that the meta model is the most accurate as possible near the best design that we have found. The other criteria could be focusing more on a global optimization or a global improvement of the meta model. So we're adding more designs where the meta model might not be predicting the outcome of the simulation very well. And then we have a convergence criteria that just says if within 3 iterations we're not able to improve on the best design that we have found so far, then we're done adapting this meta model and we're happy with the results. Of course, now the questions are, how many designs should we start out with? And there are some general recommendations that I like to follow, and that is for the start iteration, I like to use 10 times the number of parameters that I'm using. And then for the refinement process, I'm using 1 or 2 times the number of parameters. Of course, that's just a general recommendation. Always adjust those numbers as they make sense to you. In my case, I looked very closely at how I'm going to run this simulation. I was able to run 8 designs in parallel. So I had my initial design set up to be a multiple of 8. When we're now looking at the output of the sensitivity analysis, the first thing that we're seeing is, of course, a visualization of the meta model. And so we're seeing the initial meta model, and then we're also seeing the refined meta model. And we can really see how much more detail we see right around where the best design is expected to be located. For the color coding, we can also, instead of just looking at the value of the maximum differential return loss, we can also look at the local COP. So how well is the meta model able to predict the data locally? And for the initial one, we can see right around there where the best design is going to be. The predictability there is only at 85%. And as we're going through the adaptive process, the predictability is increased to 93%. The other output of the sensitivity analysis are the coefficients of prognosis. So here we can very easily see that the spacing in our ground vias is important, and also the via diameter is important. They have the largest impact on the differential return loss. The other thing to note here is that out of the 9 parameters, 2 of them aren't listed here at all. So optiSLang determined that those have so little impact on the differential return loss that they're not important enough to be included in the generation of the meta model. Another output that's important to look at is the residual plot, which really just shows on the x-axis what are the values determined by the HFSS 3D layout simulation, and on the y-axis, what was the output predicted by the meta model. And if the predictability is perfect, then all the points should be lined up on a very straight line here. Of course, that's not the case, and we have a certain scattering that occurs here. And especially the one that I want to draw attention to is the best design that we evaluated. And HFSS 3D layout predicted the differential return loss for this one to be right at minus 15 dB. The meta model predicted it to be minus 14 dB. So that shows that the meta model underestimates the performance of our differential via. The other output that I want to highlight here is the parallels coordinates plot. And when you're looking at it the first time around, it's very overwhelming. But what this one really shows is the range that each of these parameters can take on, and then the range that we're observing for the output. We can then take these sliding bars and move them up and down to really just filter out what's important to us. So in this case, what are the designs that produce the best outcomes? And here we're seeing the 105th design being the best one actually, and we're seeing how it varies throughout the design space. For some parameters, we see a small fluctuation, and for others, we see a larger fluctuation. So that again shows what input parameters have a large impact on the output. And then we can take a look at just the performance of the best design. What were the values used to produce that design? What was the maximum return loss? And then we can open up the design in 3D layout to just see how does this design perform versus frequency. Part of the sensitivity analysis is the Metamodel generation. We can then take that Metamodel and just run a quick optimization against it to see what is the best design that Metamodel predicts. So that's an analysis that's run very, very quickly. So I always recommend to run that just to, as a very quick check to see if we can, with minimum effort, improve the best design that we have found so far. Setting up this optimization is done with the optimization wizard. So it's a drag and drop operation within optiSLang, and then that wizard will guide us through the setup. Here I should mention that we're using the AMOP solver, so we're only asking the Metamodel to predict what values of the differential return loss a certain design would have. And we're using the best design from the sensitivity analysis as a starting off point. In terms of what solvers are used for the optimization, we're just going with what the wizard recommends here. And then looking at the results, we can see that, of course, the optimization ran a certain number of designs and found that the 121st design performed the best. That design was then automatically sent to 3D layout, and 3D layout evaluated that. And now we're actually seeing that the predicted value by the AMOP was minus 14 dB, and the actual design, once evaluated by 3D layout, had a response of minus 15 dB. So again, similar to what we had looked at with the residual plot, the AMOP underestimated the performance of the best design, but it did do a really good job of identifying where the best design would be located. Looking at the details of that design, we're seeing that it's actually really close to the best design that was evaluated during the sensitivity analysis. And because those designs are so similar, the return losses behaves also very similarly when we're looking at it in the orange trace here compared to the blue trace that was previously evaluated by the sensitivity analysis. So at this point, again, we want to take a step back and just assess the situation, right? We're already meeting the design requirement of being better than minus 13 dB. So we could take this design and move on to working on other projects, right? But if maybe there's some value in us exploring this design a little bit further and maybe seeing if we can squeeze out a little bit better return losses, then by all means we can do that. And we can do that in optiSLang using a direct optimization. The direct optimization that we're using here is of course target oriented in terms of finding what's the best global optimum. A direct optimization compared to the optimization that we ran with the Metamodel is of course different. Here we're always going back to the solver, back to 3D layout to give us information about how the optimization is progressing. And depending on what problem we're trying to optimize, there are different optimization algorithms available. One class is the gradient-based methods, where we're just looking at which direction does the slope point. Should we walk down the slope? Should we walk up the slope? That's one that works out really well if our solvers don't produce much noise like HFSS does. On the other side, we have the nature-inspired optimization algorithms, like a genetic algorithm, particle swarm, or optimizers like that. These ones work out really well if we have a large set of parameters, and usually we can find the global optimum, but they, traditionally speaking, require a lot of designs to be evaluated. And then as a trade-off in the middle, we have our adaptive response surface method, where we're creating a small design of experiments around what we assume to be the best design in the beginning, and then to that we fit either linear or a quadratic polynomial to predict what the designs within that small DOE would look like. And then as we're going through from one iteration to the next one, we're squeezing that search area to smaller and smaller areas until we really find the best design. This one is a very efficient approach, and that's why we're using it as the default choice when we're using optimizations in optiSLang. Setting up an optimization, again, is done with the optimization wizard. The first step when we're looking at the design space, now instead of saying something like we're just using 5% of the initial design space to narrow down our search area, we can do better than that. We can use all the information that we had gained from the sensitivity analysis. And if you think back to the parallels coordinate plot that I had shown earlier, we can take that information and import that and use that as our design space. So now we're really limiting our ranges for each of the parameters in the most intelligent way possible, right? Some of them are very sensitive. We have a small variation. Others are not very sensitive. We can have a large variation. Then in terms of which optimizer to use, we just use the one that's recommended through this optimization wizard, which will look at how long each other simulation will take, how much parameters we have. And in our case, it uses the ARSM algorithm. And now looking at the optimization results, we can see that we had to run about 220 designs. Of course, with those direct optimizations, the problems that we always encounter is that we have to run many designs because we don't know that we found the best one until we look everywhere else and we don't find any better designs. But then comparing it to the previous results, we see that we have a little performance improvement. So going from 15.03 dB down to 15.75 dB. So let's take a quick overview of what we had done here with the optimizations. We started out with sensitivity analysis that created an AMOP. And here we explored the design space, and really the primary target for that is, or the primary reason for that is that we want to find the global optimum. We don't want to get stuck on a local optimum. And then we ran a very quick analysis on the MOP that we had created to find what is the best possible design predicted by this Metamodel. And then if we require to do so, we can run a direct optimization using all the insight that we gained from the sensitivity analysis to set up the direct optimization so we can run it as quickly as possibly can be done. So let's take a quick comparison between the different simulation steps that we had taken here. And we can see that the initial design started out with -5 dB, then running 136 designs. Of course, some work has to be done to improve that. And now we're down to -15 dB. Running the optimization on the MOP doesn't cost much time. We only had to evaluate one additional design. And here we find that we were not able to improve the design, which means that we already had the best design possible found using the sensitivity analysis. And then using a more rigorous approach with a much smaller design space, we can find a better design. Here we find an improvement of about 5%, but it did take a cost in time, right? Here we had to evaluate an additional 221 designs. But all in all, this optimization approach using the AMOP is really the perfect trade-off between finding the best design possible while still gaining the most insight into the design performance and still having the most robust optimization approach, meaning we're narrowing down on the global optimum, not a local one. So now that we have determined the best possible design, what's next, right? Hopefully that goes into production. And then we have to ask the question, how do manufacturing tolerances impact the differential return loss of this optimized via? Even though it's optimized, right? Once we go into the manufacturing, none of the manufacturer devices will be perfect representation of what we had simulated here. So we want to see how a virtual manufactured family of devices, how they actually perform, and will they all meet our design requirement of having a differential return loss of minus 13 dB or better. If we have some problems with the yield, this robustness analysis will also show us what manufacturing tolerances we have to improve to increase that yield. If we're looking at a robustness analysis in optiSLang, the steps that we're following here are very similar to the steps that we're using in a sensitivity analysis. So we start off with the design of experiments that's evaluated by HFSS 3D layout. The design of experiments is generated in a different way, though. Here we're not looking at a range of the input parameters, but we're looking at a statistical distribution of the input parameters that's dictated by the manufacturing tolerances. And once we have the data evaluated by 3D layout, we fit a Metamodel to those results, and then optiSLang can very quickly tell us which of the tolerances have the largest impact on the yield of the devices. And then we also look at the results of the DOE, and we can see what kind of responses do we get. Do all these virtually manufactured devices meet our design requirement? How many of them will fail the design requirement? When we're setting up the 3D layout simulation for the robustness analysis, we have to enable other parameters, either in addition to what we had done for the optimization, or maybe just define them differently altogether. And the reason is, when we ran the optimization, we were optimizing for very specific stack-up configuration, right? The layers were fixed, material properties were thought to be constant, but once we go into manufacturing, there are certain tolerances associated with that. So we have variables defined for material properties, layer thicknesses, feature width or shrink factors associated with that. Maybe certain misalignments also have to be accounted for. Usually the way that I define the variables here in 3D layout is that I add a little delta to the already existing value. And this delta is something that describes the manufacturing tolerances. So if I have a distribution, sometimes it can be a positive delta, sometimes it can be negative delta that adds a little bit or takes a little bit away from my nominal value. And by doing a definition like this, I can have the same manufacturing tolerance variable impact other aspects of the same design. So it makes it a little bit more streamlined when I set up the simulation. In terms of how we define the manufacturing tolerances, I had mentioned already that we define them with probability density functions. And within optiSLang, we of course have different ways or different density functions available to us. The ones that I most oftentimes use are the uniform distribution, which says the likelihood of a value of minus 0.040 or 0.02, the likelihood is all equal. And I typically use those when I don't have much information provided to me from the manufacturing process. So there might be something set where the permittivity is 2.44 plus or minus 0.04. And so I use the uniform distribution because it really assumes the worst case scenario. Because in reality, usually we would see that the nominal value would have a higher likelihood than something on the outer edge. And some distribution like that is more easily described with a normal distribution, which we have a mean value and a standard deviation. I usually don't like to use the normal distribution because even though it's a good way of describing these manufacturing tolerances, some of these large values, even though they're unlikely, they could be generated throughout the DOE. And then we could run into some very strange geometry configurations that produce nonsensical results. For that reason, I like to use a truncated normal distribution, which goes into actually taking the normal distribution and then just cutting off some of the extremes. And the way I think of it is actually using a normal distribution that undergoes quality control. Because if you have a a PCB that all of a sudden has a very large thickness, even though it's not likely to occur with a normal distribution that could be set up. And then quality control would take that and chuck that design. So that's really the most often distribution that I end up using. Using the robustness analysis or setting it up, that's of course done with the robustness wizard. So like anything else in optiSLang, we use many wizards to define these kind of analyses. The first step here is defining the design space. And here we define the parameter type as a stochastic parameter, which really means based on a distribution function, randomly select a value out of that distribution. And of course, all these distributions are defined by our manufacturing tolerances. Then we create our design of experiments, and based on how many parameters we have, optiSLang will make a recommendation for what kind of sampling type to use. But really what this means is we're going into the distributions, we're randomly selecting values that that will represent those distributions to create this design of experiments. We send those off to 3D Layout, and then we get the reports back from optiSLang. So here we're looking at the histogram that shows the distribution of what are the maximum return losses of all these virtually manufactured devices. And so here I'm not only showing the actual reported values shown in these gray bins, but I'm also showing a fitted curve to this distribution. And then I'm also indicating the failure limit, which is our minus 13 dB. Looking at the statistical information, we can then see that our distribution function based on the evaluated designs gives us a failure rate of a little bit over 9%. If we're looking at the fitted data curve, we're seeing a failure rate of a little bit over 10%. And because we're evaluating only 100 or 200 designs, I much rather go with what the fitted data shows, because if we have just one additional outlier within our 100 designs, that can really impact our failure rate when we're only looking at the manufactured devices. So I always go with the fitted data in this scenario. Since we have a Metamodel, optiSLang will also tell us which of the input parameters has the largest impact on the differential return loss. In our case, we're seeing that the delta in the via diameter is causing the greatest change in the differential return loss. So this tells us the manufacturing tolerance that has the largest impact on the yield is the one that controls the diameter of the vias. And now we can start asking very interesting questions like, is the failure rate of 10.4% good enough? If it's not good enough, we know what tolerances are causing the problems. So now we can look around and see if there are other more advanced manufacturing processes available. Of course, they cost more money, but we can now start to evaluate those as well. So maybe we found one manufacturing process that really focuses on improving the accuracy of how those vias are manufactured. And here, for example, we're reducing the standard deviation of the vias down from 1 mil to 0.5 mil. Now we run another one of our robustness analyses, and we can see that our yield improved from 10.4 down to 5.8%. So that's 5.8% of the manufactured devices fail. So that's a good improvement. And knowing this kind of information, now we can ask the question, if the extra cost that we would have to invest in this advanced manufacturing process, is this going to be worthwhile for the improved yield? So with all this in mind, let's take a quick snapshot of what we have talked about today, right? We started off with an optimization approach in optiSLang, where we're really focusing on getting the most insight into the design that we possibly can get. So we started off with a sensitivity analysis with the AMOP, and here we're finding already a really good design by focusing on the global optimum and we're not getting stuck on any local ones. If time permits, and if we need to do so, we can run a direct optimization to squeeze out any possible further improvements on the design. And we're doing that with a direct optimization. And we're using all the knowledge we gain from the sensitivity analysis to set up this direct optimization as intelligently as we possibly can to ensure that that optimization runs as quickly as it possibly can. And then in the second part, we looked at, once we take this optimized via design, we go into manufacturing. What do manufacturing tolerance do to the performance of all these manufactured devices? How many of them will fail a certain design requirement? And then more importantly, what tolerances do we have to improve to increase the yield? And then we can ask the question, is the cost involved with that? Is that worthwhile for the improved yield? And with that, I want to thank you for your attention, and I want to turn it over to, I think, Sally.
Hi, everybody. Thanks for joining today. Just want to remind you that Ansys Simulation World is coming up in April. It's a virtual event. Registration starts February 16th. We'll have 5 technical tracks as well as about 6 specialty tracks, like tips and tricks on Ansys products. Anyway, keep your eyes open for more information on this. And now I'll turn it over to Saram.
Thanks, Sally, and thank you, Peter, for a great webinar. So before we get into our Q&A session, I just wanted to show all of you some of the resources you guys can leverage. Next slide, Peter. So here's just a quick schedule just for February classes. You can see right here, there's an optiSLang class this Friday that you can register at this link at the top. And keep in mind that you'll have access to this entire webinar PDF shortly after the webinar ends, and the recorded version of this will be on Ansys Learning Hub. Next slide, Peter. And here's the rest of the trainings if you're interested to go and register for in the month of February. So here's the Ansys Learning Hub, just very basic source for you guys to use, and we'll provide links for you to go and register there. And here, this is just what the links look like. And for any other support for MCAD or EES for the customer portal, once you register, you can use these emails to get support on anything that you need. We also have some embedded experts contact information here for further questions, specialty questions that you may have. So their emails are listed below. And any other further questions you can reach out to myself, Saram Zaman, or the other product account manager, Annapurna. And so now with the last couple minutes we have here, we're just going to pop into the Q&A session. So you can go ahead and throw your questions into the chat box at the very bottom, and we will do our best to accommodate you.
Yeah, and I already see one here. And the question is, what's the difference between optometrics and optiSLang? So optometrics are a way for us to set up a parametric study and run optimizations. And we also have capabilities for sensitivity analysis directly built into the electronics desktop, and that functionality can be used by by all the different solvers that live inside the electronics desktop. So HFSS, 3D layout would be some examples of that. The place where optometrics and optiSLang really differentiate each other is that optiSLang can go much further beyond just the simple optimization or the simple parametric study. So going into the robustness analysis, similar to what I had shown you here, providing much more deeper insight into how the design performs. All right. I don't know if Saram, do you see any other questions? Maybe I'm looking at the wrong panel over here.
I have one right here. Can I use optiSLang with other RF simulation tools?
Yeah, that's also a good question. So optiSLang is by the nature of it simulation tool agnostic. So if you have other RF solvers, or it doesn't even have to be RF solvers, it can be other solvers. It can be something that you've written up in Python or MATLAB. We can certainly link into that from optiSLang. So that's all possible. And I just saw another question pop up here that says, is there an example project and tutorial for today's presentation? Currently, no, it's work in progress. That's on my shoulders to provide it to you. As soon as we make that available, I will work with the Apple account team to make sure that everybody will hear about it.
Peter, we have one right here. Can I expand this optimization to a channel optimization where the channel is extracted with 3D layout and then linked to a transient circuit simulation for an eye analysis?
Yeah, so that's of course easily done if you're just sticking inside the tools in electronics desktop. So you can have the Ansys circuit solver consume the 3D layout simulation to just very easily set up an eye analysis or to produce an eye diagram. And then you can import this into optiSLang, very similar to the steps that I had shown you here today, where then the input would be geometry parameters defining maybe some of the via definitions, maybe aspects of the trace width, or maybe there's some smart ways that you can set up the routing of the channel. But that information is controlled. Yeah, those inputs are controlled by optiSLang, and then the output could maybe be something like the eye width or the eye height, and then we could optimize for that, or maybe look at how manufacturing tolerances could play a role in impacting the eye opening.
Okay, we have, can I link my HFSS simulation to my own post-processing script I typically use to extract the result values I'm most interested in?
Yeah, so that goes back to optiSLang being able to talk to all sorts of different solvers and Python scripting or MATLAB scripting capabilities. So you have something that interacts or that you usually use to extract data out of your 3D layout simulations. We can incorporate that in the simulation workflow.
So are there any other questions?
I think that's all I'm seeing here.
Okay, great, Peter. Is there anything else you'd like to cover?
That would be it for today. If you guys have any questions, please feel free to reach out to me. That can be either through the Ansys team, or if you look at the slides in a future point in time, my email address is at the beginning of it, so you can always reach out to me with more follow-up questions or additional questions about how to run HFSS and optiSLang simulations.
Thank you, Peter, and thank you everyone for attending this webinar. So that concludes the event for today. Please feel free to use all of the resources displayed today. Reach out to Peter, reach out to myself or Annapurna, and go ahead and register for training if so be. Thank you.
Thanks. Bye.
Thanks.